Good morning. Start lecture. Okay. See, my computer's giving me troubles here. Yeah, you don't see that. This appears okay from here, but it's, when I'm writing it here, the screen kind of blacked out. So, okay. Yeah, cross my fingers. Here. Yeah. So let's finish the greeting vector. Okay, and then we're going to get on to the next topic, directional derivative. Right? Yeah. Okay, so greeting vector of a function is very simple. So if you have a function of two variables, and that's basically how you calculate the greetings of that function. If you have a function of three variables, and you're going to calculate like that, right? Yeah. So this is basically a 2D, and this is a 3D here. Okay. But I need you to remember the physical meaning at here for greeting vector. We're actually going to try to prove that when we learn directional derivative. So number one is, okay, the greeting vector, okay, del f, okay, this vector, the direction is basically it points to, okay, points to the direction of greatest increase, okay, greatest increase of function f. Okay, so that's number one. Okay? Yeah. So basically, the function here, which is vector right here, it gives you a direction, and the direction points is the greatest increase of this function f. Right? Okay. And the second of all, magnitude. Okay, magnitude of this del f, okay, which gives is the rate of change. So the rate of change of f, okay, when moving, okay, in the direction of del f, okay, del f. So these are the two basic physical meanings that you need to remember regarding this greeting vector, okay, of a function f. Okay. All right. So that's greeting to function. Now let's take a look at the. I think we went over a few examples in the last lecture, and I'm going to give you in the last example, if you remember, used, let's see, a surface, for example. I use the surface z equal to x squared plus y squared as an example right here, and I demonstrated how you will draw this greeting vector, right? So the way you draw is basically you take a point on the x, y coordinates right here, okay? Then you draw that greeting vector, which is del f. Okay, basically you calculate the partial derivative of del f first, plug in this coordinates, then you draw the corresponding vector starting from that point, right? That's how you draw the greeting vector. And I was also drawing this, besides drawing this greeting vector, I also draw a contour, or the so-called level curve, okay, at here. A level curve passing through that point, right, if you recall. For this one here, the level curve is a circle, okay. So the relationship, if you look at from the top, okay, and this is the level curve, let's say for example passing through this point, and your greeting vector points is this way here, okay, greeting vector points this way. So this is easy because for the greeting vector here, so at any point it's basically 2x here, 2yg hat here, right? Okay. As you can see is the greeting vector here, picking any point, you're actually passing through this. If you extend it, it's actually going to pass through this origin at here. Okay. Yeah. Now, one of the relationships you can see now is, doesn't matter which point you take, okay? Doesn't matter which point you take. This gradient vector, okay, is actually so-called perpendicular to this level curve or to this contour. Okay, why is that? Well, this is a circle, right? This is a circle. If I have to draw a circle, and then if I draw a reading line from the circle outwards like this, right, which is basically the direction of the gradient vector right here. And if I draw a tangent line over here, right, tangent line over here, guess what? This gradient vector or this reading line here must be perpendicular to this tangent line here, right? Must be perpendicular to tangent line. So that's actually what we call is this gradient vector is perpendicular to this level curve at here, right? Yeah. So if a vector is perpendicular to the tangent line for the curve, and we see that vector is perpendicular to the curve, right? Yeah. So that's one observation we can make. And actually, this is a theory here. Okay, this is a theorem. Okay. So the theorem is we'll consider two different scenarios. Okay, one is we consider the surface when you have a z equal to f of x, y here. Then we calculate del f, right? We calculate del f. So the first theory is that del f is perpendicular to this level curve. Okay, perpendicular to the level curve. So what's the level curve? When you have a surface, how do you construct level? Level curve is f x y equal to c, right? That's the level curve. Okay. So this del f is perpendicular to level curve. Now, the other way of you seeing is this del f is perpendicular to the tangent line, okay, to the tangent line of, well, you can have many tangent lines, so we'll put a plural here, to the tangent line of the level curves, okay, f x y equal to c. So that's for a function of two variables. When you calculate the function, the gradient vector function of two variables, it's going to be perpendicular to that level curve, and also you can see perpendicular to the tangent lines. So how about the function of the three variables, right? Function of three variables. Okay. Yeah. So you can also calculate del f, right? And this del f is in a 2D plane. That's a 2D vector, and this way here is a 3D vector, right? 3D vector. So very similarly, what happens is when you calculate the gradient vector for this function three variables, the one you get is a 3D vector, and this vector is a perpendicular, right? Instead of level curve now, it's going to be what? Level surfaces. Okay. What level surfaces? This is when z, not a z here, sorry, w. I got z here. When w equal to any constant c. So level surfaces means this. Okay. That's level surfaces. Okay. So the other way of saying is, instead of saying this one is perpendicular to this level surfaces, all you can see is this del f. Okay, equivalent saying is del f is perpendicular, right? Is going to be perpendicular to the tangent planes. Okay, tangent planes of a level surfaces, basically. Is that clear? Yeah. So let's say, for example, right? If I have this surface, I'll just still use the surface over here. Still use the surface. So this surface, and this surface is I can write this surface as what? As z minus x squared minus y squared equal to 0. That's a surface, right? That's a surface. And this is equivalent thing is this is a level surface. So this is when you have a function of three variables. So when you have a function of three variables, and when w equal to 0, that's a level surface. Okay. So this this kind of paraboloid surface is basically a level surface of this function. Right? It's one of this one here. If you do let w equal to 1, it's going to be a different level surface. Right? So now, if I calculate del f, okay, remember here, okay, your del f here is this guy here. If I calculate del f, I get a 3D vector. And if, let's say, maybe I'm calculating the del f at this point in here, okay, at this point. And I think I demonstrated in the last lecture. And if we try to illustrate where the grading vector is, starting from this point, and draw that grading vector like this, right, with corresponding direction and corresponding magnitude. Okay. So this vector here points to the greatest increase of which function? This function. Okay, this function. Okay. Now, according to a theorem, this vector, is perpendicular to this level surface. Or in other words, this vector is perpendicular to the tangent plane of this surface, or to a tangent plane at that point. Okay, at that point. Does that make sense? Okay, that's basically what this theorem says. Okay. So this actually brings us to a very quick example, but I'll tell you that. But I think what I'm going to do, I'm going to try to prove this. I'll try to prove this 3D case study here. Okay, why this del f is perpendicular to a tangent plane of that level surface? Okay, well, let's just quickly prove that thing here. So let's say I have a surface at here. So let's say I have a surface, like the arbitrary surface at here. And I'm interested in a point at this location on the surface. Right. Now let's call it P naught. So there's a surface at here, and consequently I can have what? I can have a infinite number of curves, right? I can have a infinite number of curves passing through that point. Okay, and inside this surface. So what happens is there are infinite number of curves, okay, on the surface, okay, and passing through P naught, okay, passing through P naught. And we learned that for 3D curves, right, what we use is we use parametric equation to describe the curve. Okay, so let's say any of the curve here, okay, I can use the parametric equation. I don't know what it is, but suppose that this is the parametric equation for the curves in the surface, okay, in the surface here. What does x of t, y of t, z of t represent? They basically represent what? They represent the coordinates of any point on the curve. Okay? Now, this curve is not an arbitrary curve. It's a curve taking inside this surface. Does that make sense? Right? And what's this surface here? This is a 3D surface, so I'm using basically, let's say, a general function. Okay. W equal to f of x, y, z here represent this surface. Basically, this is a level surface. W equal to this guy equal to certain constant here. Right? That's a level surface, okay, of that function f. And this curve is inside this surface, meaning the x of t, y of t, z of t has to satisfy which equation? This guy here, right? Has to satisfy this. Okay, so basically, that means f x of t y plus y of t z of t equal to a constant c, right? Certain constant c. Because this curve is in the surface. Any questions? So far so good? Yeah. So now I'm ready to do my next step here now. I'm going to take a derivative of both sides of this equation with respect to t. Okay, so basically, I'm going to take a derivative of both sides with respect to t. So c is a constant, then derivative of that with respect to t is 0, right? Yeah. Okay, so this side here, it's a function f. F is a function of x, y, z, and z is a function of t. So you're taking derivative of t, so you're going to use the chain rule, right? You're going to use the chain rule. Okay? So chain rule basically says fx dx over dt plus fy dy over dt and fz dz over dt equal to 0. Okay, equal to 0. So this is what we get based on the given conditions. Very general, okay, very general. So because we're deriving a general, trying to prove that's a theorem, so we use a general case here. So for this one and here, I'm going to use a dot product to represent this multiplication set here. So the dot product basically we're using is one vector is this, the other vector is that, and the other vector is this. Okay, all right, that's dot product. And now you observe, what are the two quantities at here? What's the first quantity? What is this first quantity? The gradient. That's the gradient of the function f, right? It's gradient of function f. What's the second quantity here? This is a derivative of what? R. Look, this is R here, right? This is basically derivative for R. So what does that tell us? It tells us the dot product of the gradient and with the derivative of the parametric equation R is 0. So we learned in the multivariable function, what does the derivative of parametric equation represent? Velocity or tangent vector, right? Okay, so basically means derivative of this R means you're taking as the tangent vector. Now, what I'm giving it here is a general parametric equation. Basically, I'm saying this can be used to represent any curves on the surface. So it can be used for this curve. It can be used for this curve. Is that right? So which means this guy here can be used to represent a tangent vector for this curve at this point. Can also be used a tangent vector for this curve at this point. Okay? Does that make sense? Okay? So this is a tangent vector. Okay, this basically represents tangent vectors. Okay? So tangent vector to what? Tangent vector, this is tangent vector to the curve, right? To R. Okay, to R. However, you also need to notice, where's R? R is in the curve, in the surface. Right? This R is in the surface. So if this is a tangent vector to the curve in the surface, and this is also a tangent vector to the plane, to the surface, right? To the surface. So this is also the tangent vector to surface. The F equal to C. Okay, F equal to C. Okay. Now, when you have a two dot product equal to 0, geometrically that means what? The two vector perpendicular. So basically means del F is perpendicular to this guy here. Okay, to this guy. To what? To any tangent vector at the point P naught to the surface. Does that make sense, right? Yeah, to any vectors. So if this vector is perpendicular to any vectors at the P naught of that surface, so that means this vector is perpendicular to the surface. Okay, so which is basically the theorem of this one here. Okay, the theorem of this one. Okay. And you can use similar strategy to prove this one here too. Right? Okay. So that's basically one of the things that you need to remember this all the time, because it's very useful results. Okay, very useful results. So a direct application of this of this theorem is this. So one of the application is, so let's look at the example, okay? The application is, what is the tangent plane to a surface at a certain point? Is that clear, right? So the question basically is, what is the tangent plane to a surface, okay, at a point? That's basically one direct application at here. So I'll give you the general formula first, right? And then we'll look at a specific example here. So we're talking about general surface here. So let's say y, z equal to c. Okay, that's a surface, right? That's a surface. What is the tangent plane to a surface at a point? Let's call it point P naught, x naught, y naught, z naught. So that's, if you have this function and you have this point, and then you're trying to look for tangent plane. So what do we do? Well, back to the old school, you know, what is the equation of motion? No, not motion. What is the equation governing a tangent plane? Or what information do you need to find in order to find the tangent plane? And in order to find a plane equation? Normal vector and a point, right? Do you have a point? You already have a point. And then what's the normal vector? Gradient. Right, gradient. Normal vector meaning you're trying to find a vector perpendicular to the plane. And that plane is tangent to the surface at a point, so natural choice is this guy here. Okay, this guy. So then let's try to calculate this, write down this formula here. So normal vector is del f. Now this is not arbitrary del f, this is del f at this P naught, right? At this P naught. So if I calculate this out, it's basically fx at P naught. Maybe, but just use P naught here. I hat plus fy at P naught and fz at P naught. Okay, so that's a normal vector. And you have the point. Now I'm ready to construct my my plane equation. So plane equation meaning the del f here, these three things are the what? Are the normal vectors. So they're the coefficient, right, for the plane equation in here. And plus okay, that's the plane equation, right? That's the plane tangent to the surface at the point x naught, y naught, z naught. Okay. Any questions? Yeah. So how about, this is one application here, right? This is one application. How about the next natural question here? What is the normal line what is the normal line to surface at point at P naught? Right, that's another easy question you can solve right here. So you have a surface right here, and here's the point. Can you construct a line that is normal to the surface? So that's right. So what information do you need? You need a point on the line, and you also need a yes, right, parallel vector, which is basically del f here. So I think that you can write down the line equation immediately. So x equal to x naught plus fx p naught t, and y equal to y naught plus fy p naught t, and z equal to z naught plus fz p naught t. Okay. let's see in a specific example here. So I'll give you a surface, and let's try to find a tangent plane. So here's the surface, here's this P naught. Okay, so there's no trick here at all. And you need to basically use this formula here. Okay, use this formula. So here's the surface. Now you need to be careful. There's one thing in here. Okay, you know when you try to solve anything here, you always go back to the general rule at here. And the rule here is here's a surface. So a certain function equal to constant c. So then you look at this one here. You know, that's exactly the format we have here, right? Exactly format. So that's perfect. That's good. So basically, this whole left side here is your fxyz. Okay, fxyz. So then the rest of the work is calculating the grading vector and then plugging it into this plane equation. Okay, it shouldn't take you more than 15 seconds here to finish this. So at where? At the P naught. Okay, at P naught. Del f means partial f over x, partial f over y, partial f over z. So this is a simple one here. So 2x at the P naught, 2y at the P naught, 2z at the P naught. So plugging this x, y, z value, which is 4, 2, 2. Okay. 4, 2, 2. 4, 2, negative 2. So that's the normal vector. And all you need to do now is just plugging over here. Okay. Alright? So you do that yourself, okay? Try to find it. So I'm my end function is, my end plane equation is this. Okay, is this. Okay? Yeah. Any questions? Okay. Now one of the slight variation, okay, one of the slight variation which I find that some people got tricked during exam is this. Instead of giving you a surface like this, I said surface so I said let's do surface is this. Okay, here's a surface. Can you calculate the tangent vector? Yeah. Why is it equal to 8? Because it's okay. I skipped a step here, so that's my intention. I was trying to. So you're plugging your 4, 2, negative 2 over here, here, right? And you're plugging your 2, 1, 1 over here, here. And then you expand the 3 terms that are here and move all the constant to the right side. That should be 8. Yeah. So try it out. Okay? Try it. Actually, I see lots of students got the number 8 wrong. Well, not necessarily 8 in the exam, but many students got the number wrong when during exam settings. Okay, yeah, that's a common mistake actually sometimes. Is that clear? Yeah. So let's say I'll give you this surface here. How would you calculate the normal vector of a tangent plane at a certain point? Suppose that I'm still going to use this point here. Okay. Yeah, who said that? Yeah. That's excellent. You have to move everything to one side first. Why is that? Well, rules, right? Here's a rule. The rule is a function of x, y, z equal to a constant. Does that look like the rule that we have there? No, right? Yeah. So what do? We move everything to one side. How do you move? Whether you move the z to the other side or move this to one side, that's all okay, right? But you need to do one of these things here. Okay, you need to do one of these things here. And then this is going to be your f, x, y, z. Okay, this is going to be x, y, z. And then you calculate del f. Okay, yeah. So you can try that yourself, right? You can try that. Any questions? Okay. Yeah. So this is basically the cutoff point for the midterm. So midterm will test up to this moment material. So from the vectors, lines, planes. What else? The derivative vectors, functions, multivariable functions, partial derivatives, total differential, line integral, arc length, and the grading vector plus the planes based on the grading vectors. Okay, so those are basically materials. Yeah. This just a rewrite of this original one here. So first of all, this is a surface, right? No, I moved this term to the left side. Yeah. Was that good? Yeah. Okay, so no, again, no formulas. I know some of you asked for, but I think midterm, I want you, there's less material, so I want you to, if there's any formula got involved, for example, if what's the formula for line integral? It's easy, right? Just write 5 or 10 times, you memorize that. There's not many formulas so far. If there's any very complicated integrals or derivatives getting involved, I generally will put that in the exam paper, right? For example, what's the derivative of inverse tan kind of function, right? Okay. So you shouldn't worry too much about the calculation-wise. What you should worry about is, first of all, what's the procedure of doing certain question properly, and how do you do derivative integrals for simple cases? Simple cases means substitution technique. So I can't get away from integrals, right? We're not just testing you how to use a formula. So you have to be able to have the computation skill to do it right. And what's the integral by parts? Well, usually integral parts is not that difficult if you have an exponential or sine get involved to use that integral by parts. Okay. All right, so any questions? All good? All right, so we have one more thing here regarding this grading vector here. Now, if you recall that in previous lecture, last week lecture, last Tuesday lecture, when we were talking about multivariable calculus, and we were talking about partial derivative, the last topic we talked about is the linearization of a certain surface or certain function of two variables, right? Yeah, that's what we talked about. So we derived a certain equation for that. So that now here I can use the grading vector to do the same thing here, right? So I'll use an example here. So let's say I have a surface. I'll use a general example. Suppose that I have a surface here. Okay. And the general question in that lecture is, what is the linearization of this surface at a certain point? Oh, I'm kind of worried this computer will last me until the end of the semester here. What's the linearization of this function at certain points here? Okay. Yeah. Pardon me? Exactly. Yeah, you just create a plane, right? Because we know it's going to be a plane to approximate this surface at that point. So the whole question is to construct a plane at this point here, right? At this point. So let's construct a plane here. Okay, let's construct a plane. It's like a general question for this kind of example here. Huh? Yeah. So remember the first thing, what we do, the first thing is we move everything to one side here, right? Okay. Then we calculate, let's call this W here, call it W. Then we calculate partial derivative of this function, okay, this function. So one of the things I think maybe some of you is confused is, so sometimes you have F, sometimes you have a W, right? Well, you got to look at the specific situation here, because this situation Z equal to F, so F is already being used. F is a function 2 variables, so I have to use a W. I can't use F at here anymore, right? Yeah. And the plane we're looking for is del W at P naught. Okay, first calculate this one here. So what's the del W at P naught? Well, del W meaning partial W over partial X. And partial W over partial X is actually just simply partial F over partial X at P naught. Partial W over partial Y, meaning partial F over partial Y over at P naught. Partial W over partial Z, Z is just Z here, which is going to be 1. Okay, going to be 1. So I skip one step here. Is that okay? No? Okay, let me rewrite it here. So this is supposed to be a step here, right? So this step here is partial W over partial X at P naught, partial W, partial Y, P naught, partial W, partial Z at P naught. Okay. So you look at this one here. Here's your W. Here's your W, right? Your W. So when you take a partial W over partial X, here there are two terms in the W. Two terms. The first term is Z, and Z is not a function of Z is not a function of X. So only the second one is a function of X. So that's why negative partial F over X. Second one, similarly, partial W over partial W. And Z is not a function of Y, so this just basically negative partial F over partial Y. And the last one here is partial W over partial Z. And F is not a function of Z. Only Z is a function of Z itself. And partial Z over partial Z is 1. Okay? Yeah. Clear? Alright, so now I got my normal vector to the plane. Then all we need to do is to use our plane equation now. So plane equation saying is negative fx, this is this term here, at P naught, multiplied by x minus x naught, minus fy P naught, y minus y naught, plus this 1, z minus z naught, equal to 0. Alright? So that's the plane equation, the tangent plane equation to the surface, which is the linearization of the surface. So this is a linearization or approximation. Now, I don't think I'm going to stay at this expression yet, so I can simplify this just slightly. So you can see this term here is 1 multiplied by z minus z naught. That's basically z minus z naught, right? And this is z minus z naught. So I'm going to basically just leave the z to one side and move everything else to the other side. Okay, to the other side. So if I move everything to the other side, then what do I get? I get this is z naught. This is a negative here. When you move it to the right side, it becomes positive, z naught. And these two negative becomes positive too. So that's fx p naught x minus x naught. Fy p naught y minus y naught. Right? So that's basically what happens after you shift everything to the right. So the z naught, what's the value of z naught here, right? What's the value of z naught? Well, your original, what are we trying to linearize? We're trying to linearize this function here. Linearize this function. So z naught is basically f of x naught plus y naught, and plus the rest of the term, right? So this term. Okay. Yeah. So if you look at this one here, look at this one here. And then if you look at the notes that we had on the previous lecture, that's exactly the same results, right? That's exactly the same result. So this is basically the linearization of that surface z equal to fxy at the point p naught. Is that good? Okay. All right. So now we talk about grading vector. Now, okay, we talk about grading vector. And before we move on, let me ask you a question here. So, talk to your neighbor first. What's the physical meaning of grading vector? The two things. Number one is what? And number two is what? So we'll focus on number one there. Okay. So correct me if I'm wrong, and the grading vector points to the direction of the greatest increase of function f, right? So I guess I'm right. So grading vector, here's the grading vector. Here's the function f. So it points to the greatest increase of this surface f here. So in other words, okay, you got to move into this direction in order to have the greatest increase of this surface, which is, of course, it's going to increase in this direction here, right? Okay. So now the simple question here is, I'm going to ask you is, so what happened when you're at a minimum or maximum location of the surface? What is zero? What magnitude? What's zero? Grading vector is zero, right? Is that you have a question? Yeah.
Yeah, I was going to ask, kind of relating, I guess, to what you just said. So when it gets to the point, because it's a vector, when it gets all the way up to the best point,
Yeah.
turn around, or like what does it do?
Turn around? Oh, you mean you're at the maximum point, you turn around?
Well, if it gets smaller and smaller, as you reach the maximum, and you're like, you have to let one end.
Yeah. So if you're at, well, this is a sort of a limit concept. If you're at the maximum or minimum location of the surface, right? So first thing is you need to understand this guy equal to 0 now. So del f equal to 0 at mean or max, okay, location of f. Okay, yeah. Not parallel, 0. A vector 0 basically means 0, no magnitude anymore. Right? No magnitude, no directions, is 0. But once you start to move a little bit to this side, to the other side, then you will have a certain direction. Depends on the type of surface. Is that clear? Right? See, remember the one I told you to tell your neighbor, right? First is, it tells you is the direction, the greatest increase of the direction of the surface. What's the second? The second one is the rate of change, right? The rate of change of the surface. So if you're already at this location minimum, maximum, and the rate of change is basically 0. Yeah.
If it's a vector that means you can like go on to across that line though, like when it's attached, so
Come again? It's a vector attached to a line. Which line?
like your del up there is pointing away from the curve, but it's tethered at z. So eventually when it gets far enough away, this vector just disappears.
Sorry, I didn't quite get your question. Let's say, for example, here's a minimum point here, right? Here's a minimum point. If I'm going to here my gradient vector at this location, del f, in the other way, the del f will be 0. Okay. So what's your point? What's your question? You have a line. What line you're seeing? So maybe you can come to me after class, right? We'll talk about it. Okay. Yeah. Okay, so this one points the greatest increase of direction. So the natural question here is, what if, so let's say you have a little guy here. What if this is not moving into this direction? What if it is moving in this direction? Or what if it's moving in that direction or that direction, right? So the same question you should ask is, if it's moving in any direction starting from this point, what would be the rate of change of the surface or the function f? Is that a legitimate question, right? Yeah, that's a natural question, basically. So if you're moving at a different direction, and what would be the rate of change of this function f or the surface? So essentially, when this guy's moving here, and this guy will move accordingly. Okay. But because this is moving at a different direction, then the rate of change for this little guy here will be different. And the rate of change of this little guy basically represents the altitude change or the height change of the surface. Makes sense, right? Yeah. So now this kind of natural question here is, we're bringing is the direction, right? It's a direction walking. We're actually also bringing the second one here. When you're talking about rate of change, when you're talking about rate of change of certain function, it's basically a concept what? In single variable rate of change of certain function, you call that slope, right? So you have a rate of change of a certain function. Basically, it's a slope concept. Okay, slope concept. So essentially, we're looking for is, right? What is the rate of change of f? Okay, when walking to an arbitrary direction from, let's say, a p naught here. Okay. So we're going to be I'm using a function of two variables, for example. So I'll ask this question here. Okay, this question. So let me re-sketch it here. Okay, let's re-sketch it here and look at this. Look at this question here, or trying to solve this objective. Okay, so I'm going to re-sketch a surface. So I have a surface at here, and I have a point P naught at here. Okay, I have a point P naught. Now, what we're going to do is we're going to try to draw an arbitrary direction walking, right, starting from P naught. So let's say it's going to walk in this direction here, walk in this direction. Now remember, when we're talking about direction, if I use a vector to represent a direction, I just simply have to use what? A unit vector, right? So I use a u hat at here to represent the unit vector, to represent the direction of walking, okay? Direction walking. So in other words, there's going to be a slight change starting from P naught in this direction, okay? In this direction. And at the P naught, you probably at this z naught at here, right? At z naught here. And this is a surface z. Okay, this is surface z. So I can think of this scenario as this. Essentially, when you're walking along the U hat from P naught, so the trajectory is basically a line, right? It's basically a line. Okay, so let's call it L here. Call it L. Okay, call it L. So now imagine the situation here. Imagine the situation. As this little a at here is walking in the U hat direction. And what happened to this little b at here? So it's going to change, right? It's going to change. So how is that going to change, and what kind of a curve is going to be traced out? That's right. It's going to be a curve between a plane passing through the L and the surface here. Does that make sense? So if I draw it out, it's going to be at the intersection of this plane and this surface. So that's going to be a curve probably looking like, let's see, this. Okay, looking like this. Yeah, I have an animation file. If I have got time, I'll show you there. But I think this is kind of straightforward. You know, as you're walking here, that guy's walked basically controlled by the A here. It's going to change along the surface and also along this curve, which is intersected by this plane and this surface. Right? Yeah. Bear in mind the question here, right? The question is, what's the rate of change of f when walking in the arbitrary direction? In this case, is U hat here. So the rate of change of f now in this scenario is basically the rate of change. Instead of saying rate of change of f, it's actually rate of change of what? Of this curve. Does that make sense? No? Well, because your little guy b is not going anywhere except where? This curve. So if you have a change in around the p naught, how is this b change? This b is going to just change around where? Along this curve. Does that make sense, right? So we're talking about rate of change of f. It's basically equivalent to saying rate of change of this curve here. Yeah.
Is that when the x is constant?
No. I'm arbitrary direction, not just x is constant. Right? See, if I walk in this direction here, is the x going to be constant? No, right?
Why?
Because let's say this is 1, 2. Now the next time maybe it's going to be 2, 3.
But it's going to be constant.
No, z is not constant. Z depends on this function here. Z is going to change, right? Z depends on the function. Maybe this is a function of this, for example. Is it going to be constant? No, right? Yeah, it's going to change. Okay. So now the thing is here basically is I'm going to try to generalize the situation here. So I'm going to indicate use a positive s. Use a positive s to represent is the positive direction of a displacement. Is that okay? Right? Positive displacement. And now I'm going to introduce the idea of the slope now. We all like the slope, okay? So the rate of change of the curve is basically the idea of what? Slope. The rate of change is the slope of the curve. But the only question here, our original slope is in which plane? We're talking about xy plane, right? Oh, sorry. Yeah, xy plane in a 2D. But I don't have an xy plane now, right? What plane do I need? So I need to construct myself a plane. So what plane do I construct? I'm going to construct myself plane. The vertical is a z. Because why? Because there's z change, right? There's z change. The horizontal is which one? This guy. Okay, this guy. So I'm going to construct myself a plane of this. Can you see that? See, this is a z here, right? This is z. This is s. So that's essentially, it's like a xy plane representing this plane here. Okay, representing this plane. And this plane contains this curve here, contain this curve. So if I look at this curve here, and you know what, I think I'm going to try to this. So I'm going to use a blue, not blue color, I don't have a black color. Yeah, black color. I'm going to use black color for this, red color for this. Okay. Yeah, my screen kind of or so this is a red. This is a black. This is red here. Okay, this is red here. Was that okay? Yeah. Now here's the S. Here's Z. Now remember, when you construct you're trying to construct coordinate system, the coordinate system has to satisfy the right-hand rule, which means the Z has to be here, the S has to be here. So you cannot have a coordinate like this. Okay, you can't have that. You have to be this. Okay. Now, if I have this one here, I'm going to draw this curve inside this plane here. Okay, inside this plane. Okay, use your color here. So where's the red color? Right. So basically, it's like you're looking at from this direction here. Right. You're looking at from this direction. Okay. So when you're looking at this direction here, where's my red color? This is already red, isn't it? Right. So. Yeah, my computer. Blue first, and red next. So I'll try a certain kind of general thing here. Let's see. This is probably the red portion in here. Okay, the red portion. That makes sense. Okay, and the other side is no. The other side is black, right? That's what it looks like. Does that make sense? Yeah. So this is what happens when you look at this direction. Why am I looking this direction? Because I'm walking this direction here. You hat. Okay? Walking this direction. Right. So now, if you look at this direction, look at this one here. Look at this one here, right? Based on my drawing, okay? Based on my drawing, when you're moving from P0 to this direction, and this B at here, guess what? Is it gonna increase or gonna decrease? Increase. So if this is a corresponding point B, the little guy B at here, and when you're walking to the positive direction of S at here, okay? So you have a slope right like that, right? Right like that. Okay. Was that all right? So when you look at the slope at here, like in XY plane, when you have a line with a slope like this, what do you call it? Positive slope or negative slope? Negative? Positive, right? Positive, because the angle here, right? Positive. So that's absolutely good, because we said it's going to increase, right? That's a positive slope, basically. Okay? Yeah. So now, before we go on to the mathematical expression here, let's think about the other scenario. Okay, the other scenario. What if it's not walking this direction? What if it's walking to that direction? Okay, what if it's walking to that direction? So if it's walking to that direction, then what is the positive direction of displacement now? Instead of here, it's going to be this, right? It's going to be this. So in order to construct the plane, I'm not going to look at this direction now. I'm going to have to look at from where? From here, right? From here. So because why? Only when I'm looking from this side here, I will have a coordinate system like this. Does that make sense? Yeah. Visualize that, right? Only when you're looking from this side here, you can construct a coordinate system Z and S like this. Because if you're still looking from here, the S, right? If you're still looking, hang on a second here. What's going on? Oh, shush. Anybody want to correct me at here? I guess I all screwed up here, right? So it's actually the red part should be this guy here. The green one should be this one here, right? Yeah. So this is the green eye. Okay, this is the green eye here. Okay, and this is going to be the red eye. Okay, this is going to be the red eye here. So if I have the red eye here, where's the red portion? The red portion, instead of over here, the red portion is over here now. And the black portion is over here. Black. Is that black? Yeah, that's black, right? Is that good? Yeah. Sorry about confusion. Here is my computer. Okay. Any questions? Great. So if I'm in the red eye here, if I look through the red eye here, and now where's the person B? The person B is at where? Here. Right? That's the person B. Okay, that's the person B. Now if you're walking in a positive direction, you had this direction here, which is basically this direction. Look at that. That B is going to decrease, right? The B is going to decrease. Okay, that's exactly what happens right here. Okay, so you're going to have, if I use a slope at here, you're going to have a negative slope at here. Okay, you're going to have a negative slope for this curve. Okay, any questions? All right. So now enough red eyes, green eyes. Now let's talk about math here, right? The math. So if you have an xy plane, what's the derivative? You use what? dy over dx, right? dy over dx. But now what do I have here? I have a zs. And I'm trying to describe the concept of a slope. Guess what? What will be the slope now? dz over ds. Well, the z here is from here, right? It's from here. Z equal to fxy. So instead of z, I can also say it's a df over ds. So this is the slope concept, right? This is the slope. Okay, slope. Would that be all right? However, this is a special situation. Just df or ds doesn't give you all the information. The information that here is you're walking in a certain direction, u. That's what gives you the positive s direction. So instead of writing this one here, we'll write df over ds with the subscript u hat. Okay, the subscript u hat. So that's the slope. That's the slope we're talking about when you're walking in a direction of u hat. And to be more specific, you can put another p naught at here, which represents the slope when you're walking along the u hat at the point p naught. Is that clear? Okay. So what I have just written here is basically the so-called directional derivative. Okay. This is basically a directional derivative. Okay. Let's call it dd at here. Okay. So that's directional derivative. It's a derivative concept, it's a rate of change concept, and it's a concept when you are moving along certain directions starting from point P naught. Okay, yeah, that's it. So there's another way of writing this one here. It's equivalent. They write it like this. So there's a capital D here, U hat F at a certain P naught value. That's the equivalent notation. Okay. So in other words, the physical meaning basically what it says is, okay, what does it give? It gives you the rate of change of f, okay, at the p naught in the direction of u hat, okay, of u hat. U hat is a unit vector, okay, unit vector. So how do I calculate this guy then? Right? How do I calculate this? So now we understand the physical meaning. We understand the notation-wise. So how do we calculate this one here? So now let's start from the basic definition of a derivative. But before that, let's give the u hat a certain quantity here. U hat is a vector, it's a unit vector. So let's say u hat is a I hat b j hat, right? So that's u hat. So we're restricting ourselves to the 2D plane, but you can easily just expand everything in a 3D plane, or even multi-dimensional. Okay, so if you recall that derivative, when you have df over dx, what was that? What's that? Limit delta x, and then f x plus delta x minus f of x over delta x. That's the derivative of a single variable function, right? Now, I'm talking about derivative of this thing here, derivative of this. So then this is a function of two variables. So then the definition using similar like this is going to be this. Okay, so use this notation in here. Okay, equal to limit. Okay, a small quantity of h go to 0, and f x plus ah y plus bh minus fxy. That's the definition. Okay, that's the definition here. Let's see if that makes sense or not. Okay, let's see if that makes sense. If that satisfies the meaning of a derivative. Okay. So you look at the first quantity here. xy basically is the current point you're interested. Okay, it could be x naught, y naught. And what do? You vary the x and y. Just like here, you vary the x with a small quantity. You vary the x and y with a small quantity. One is ah, one is bh. Why do you vary that? Why do you vary the x and y according to that? Because we're talking about the change in the direction of u hat. Right? Direction u hat basically means the x will change with a multiple of a. The y will change with a certain multiple of b. If you're currently at the x here, then the next step is going to be x plus certain multiple of a here, right? So that's why here x plus ah, y plus bh. So that represents a small change of this original x, y, and in the direction of u hat. Okay. Was that right? Okay. So that's exactly kind of similar concept here. So there are two ways. I guess this is still not good, right? I mean, you can't take a limit every time when you try to do this derivative. So we need a better expression here. So I'll give you the better expression here. Okay. Okay, that's it. That's another way of calculating the directional derivative. So what is this in here? This is what we just learned. The gradient. The u hat is the direction, unit vector. So when you're trying to calculate the directional derivative at a certain point, actually it's quite simple. Just this vector dot this vector. That's it. Okay, that's it. Now, how do I prove this one here? There are two ways of proving this one. One way to prove is through this definition. It'll end up here. And the other way of proving this one here is the way that, you know what? Let me just, it's very simple here. Let's just use this proof here, okay? Yeah, proof. So we're trying to prove this one, okay? Trying to prove this. Okay, so this is df over ds, and I'm going to use the chain rule. Okay, I'm going to use the chain rule. Because f is a function of x and y. And you're moving with the displacement of s along direction of u. So that means the x and y will be a function of s. So that's a chain rule here. Okay. And these two at here, I'm going to write it, right? This is dx over ds, this is dy over ds. So how does x and y change? Right? That's the question here. How does x and y change? Okay, how does it change? Well, they change, right? They change basically along which direction? U hat, right? They change along U hat. Like the one I draw here. Like the one I draw here. How does x, y change? It changes along which one? Along this a line, right? They change along the line L. So basically, the trajectory of x and y, in this case here, right? If you keep walking along U hat, it's a line, right? It's a straight line. So the natural question is, what is that the straight line equation? What's the line L equation? How do I find the line equation? A point on the line and parallel vector. Do I have a point? I have the point, right? P naught. Do I have a parallel vector, which is? What's the parallel vector? Not a gradient. U hat. Right? So U hat is the parallel vector. So the line is basically x equal to x naught plus U hat, right? The U hat I'm writing it here is AI plus BJ. So this is going to be A, I use S at here. Y equal to Y naught plus ES. Okay? That makes sense? Right? That's the line L equation. Okay? That's the line L equation. So now you can see now what's the derivative of dx over ds? I'll give you dx over ds based on here. Hey. And what's the derivative of y over ds? Hey. So then this expression right here is equal to fx a plus fy b. Okay? And I'm going to write this one in a vector dot product format. Okay, same thing. The first one here is del f. The second one here is U hat. Okay? So that basically give us a proof as this guy here. Right? Is that good? Yeah. So that's the direction derivative. And if the question is simply just asking, what's the direction derivative of a certain function at the certain point? All you need is just this formula. It's very, very simple, right? It's quite simple. Okay? Yeah. But we have a couple of properties we need to basically understand this directional derivative here. Basically, what is the relationship between this del f and the U hat? So we're going to cover that in the next lecture, but for the time being, bear in mind of what are two things here, okay? What's the two things? U hat is the direction of walking. Del f is what? The direction of pointing to the greatest interest function. So, okay, yeah. Any questions?